Welcome back, math friends. This is AP Calculus, section 2.3, day 1. Today we're going to begin by talking about what our limit laws are and how these limit laws can help us either simplify or evaluate expressions containing limits. You may remember these from chapter 12 of pre-calculus if you covered that material last year. But the following limit laws are most of the time pretty intuitive. The limit of a sum is the sum of the limits. So if you're adding two functions together, the limit as x approaches a would be the limit of those two functions evaluated at a added together. The limit of a difference is the same concept. The limit of a constant multiple says that you can take this c value and you can bring it out in front of the limit. The limit of a product says that you can evaluate the limits of each function separately and then multiply those two things together. The limit of a quotient is the same idea, keeping in mind though that with the limit of a quotient we do have this caveat that the limit as x approaches a of g of x cannot be 0, and that is because that limit is the one that is in the denominator and we can't have our denominator 0. Limit of a power says that you can evaluate the limit and then raise that to the power and get the same result. Limit of a root says that the limit of a root is the root of a limit, meaning you can evaluate the limit and then take the root of that, get the same result. And then down here, number 8, we have the limit of a composition, which says that the limit of a composition is the composition of the limits. The first couple examples here where we have some work to do are just some of our special limits, but these are some pretty straightforward examples. The first one, the limit as x approaches a of c is c, which basically just deals with a constant function. So if we had a horizontal line and we said the limit as x approaches 2 of 7, well, that's going to be 7, right? Because it's always 7 if it's a horizontal line. Limit law number 10, the limit as x approaches a of x to the nth power will just be a to the nth power. So the limit as x approaches 4 of x cubed is going to be equal to 4 cubed, which is 64. Number 11, the limit as x approaches a of x is just a. So the limit as x approaches 5 of x is 5. And then finally, the limit as x approaches a of the nth root of x is going to be equal to the nth root of a. But it says where n is a positive integer and a is greater than 0. So keep in mind, a is our radicand, and whenever we take a root, we can only take even roots of positive numbers. We can't take even roots of negative numbers. So that's why this rule is just saying that a has to be a positive number or a number bigger than 0. So the limit as x approaches 8 of the cube root of x is just going to be the cube root of 8, and the cube root of 8 is 2. Continuing our practice of the limit laws, let's take a look at the following examples. We're given 3 limits at the top. The limit as x approaches 2 of f of x is 4. The limit as x approaches 2 of g of x is -2, and the limit as x approaches 2 of h of x is 0. So given those 3 pieces of information, we're supposed to apply those to the following examples. In letter A, we're asked to do the limit as x approaches 2 of f of x plus 5 times g of x. And basically we know that based on our limit laws, this would be the limit as x approaches 2 of f of x, which is 4, plus 5 times the limit as x approaches 2 of g of x, which is -2. And 4 plus 5 times -2 is -10. 4 plus -10 will give us an answer of -6. Letter B, the limit as x approaches 2 of g of x cubed, we know that we can do the limit as x approaches 2 of g of x. We can take that, which is -2. And we can cube it, which gives us an answer of -8. Letter C, the limit as x approaches 2 of the square root of f of x. We know that we can take the limit as x approaches 2 of f of x, which is 4, and we can square root that, and our answer is 2. Letter D, the limit as x approaches 2 of 3 times f of x in my numerator. Okay, so I do 3 times the limit as x approaches 2 of f of x, which is 4. And then on the bottom, it'll be the limit as x approaches 2 of g of x, which is negative 2. Now I just do the math. 3 times 4 is 12, and 12 divided by negative 2 is negative 6. Letter C, the limit as x approaches 2 of g of x divided by h of x. Well, that's going to be the limit as x approaches 2 of g of x in my numerator, which is negative 2. And then it's going to be the limit as x approaches 2 of h of x in my denominator, which is 0. But now we run into a problem here because we know we can't divide by 0. So that means that this one does not exist. And then finally, letter F, we've got the limit as x approaches 2 of a product in the numerator and then divided by f of x in the denominator. So we just do, in the numerator, the limit as x approaches 2 of g of x, which is negative 2, times the limit as x approaches 2 of h of x, which is 0, divided by the limit as x approaches 2 of f of x, which is 4. But if we have 0 in our numerator, 0 divided by anything is 0. So the answer is 0. Example 2 gives us a graph and asks us to use the limit laws and the graphs of f and g to evaluate the following limits if they exist. Before I even start, I'm going to do a little bit of work on my graph here just to make it easier to read, because sometimes it's a little hard to count, so I like to darken my x-axis and my y-axis. And on your paper, you might want to color code your two functions. F is the pink function. There's a hole right here with a closed circle right there. And G is the blue function. And there's a closed dot right there and an open dot right there, just to call attention to those details on the graph. All right, so beginning with letter A, using the limit laws, I know that this expression is going to be equal to the limit as x approaches negative 2 of f of x plus 5 times the limit as x approaches negative 2 of g of x. Now I need to use the graph to determine what those things are. Well, x equals negative 2. That's this line right here on my graph. So as x approaches negative 2 on our f of x function, remember to evaluate a limit, I have to look at both sides. So as I am approaching negative 2 from the left, and as I am approaching negative 2 from the right, the function is approaching a value of 1. Now remember, based on the definition of a limit, it doesn't matter if the value of the function is actually 1. What matters is that both sides from the left and from the right are approaching 1. So right here, this is going to be 1 plus 5 times, now I have to do the limit of g of x as x approaches negative 2. So from the left and from the right, it looks like the value of g of x is negative 1. So then I do the math. 1 plus negative 5 gives me an answer of negative 4. Letter B, according to the limit laws, I am going to take the limit as x approaches 1 of f of x. And I'm going to multiply that times the limit as x approaches 1 of g of x. So now on my graph, I'm going to be looking at x equals 1, which is this vertical line right here. On our f function, as x is approaching 1 from the left, and as x is approaching 1 from the right, the left-hand limit and the right-hand limit agree, and they agree that f is converging on a value of 2. So this is going to be 2 times, and then the limit as x approaches 1 of g of x, here's where we have a problem. From the left-hand side, the graph is approaching a value of -2. From the right-hand side, the graph is approaching a value of -1. So this right here, this limit does not exist. And when you multiply 2 times something that does not exist, you have a limit that does not exist. And then finally, letter C, we are doing the limit as x approaches 2 of f of x divided by g of x, which is going to be equal to the limit as x approaches 2 of f of x in my numerator, and the limit as x approaches 2 of g of x in my denominator. So then when I look at x equals 2 on my graph, one more vertical line here. When I look at x equals 2, it looks like as x approaches 2 from the left on f of x and from the right on f of x, my values agree, and looks like it's right between 1 and 2, so I'm just going to go with 1.5. And then g of x, from the left and from the right, they agree, and it looks like the function is going to 0. Uh-oh, but anything divided by 0, we're undefined, right? So for this one, again, we can say can't divide by 0. So if this is the case and we're trying to figure out a limit, we would have to say that this limit does not exist because we cannot divide by 0. The next thing we're going to talk about is evaluating a limit by direct substitution, which basically means that if they're asking you to evaluate the limit as x approaches 2 of x squared plus 2x, well then you just plug in 2 for the variable, you do the math, and you see what you get for an answer. The direct substitution property says if f is a polynomial or a rational function, and a is in the domain of the function, then the limit as x approaches a of our function should be equal to f of a. For example 3, we are just going to plug -2 in because -2 is a polynomial function. It would be a very big polynomial if we multiplied it all out, which we don't need to do to evaluate the limit. So this is going to be equal to, now I'm going to be careful here with my notation because I've got exponents. So -2 squared plus 1, that whole thing to the third power, times -2 plus 3 to the fifth power. All right, and again, we work with PEMDAS here. So we start on the inside, we work our way out. We've got -2 squared, which is going to be +4 plus 1 cubed. And then we have -2 plus 3, which is going to be +1 to the fifth. 4 plus 1 is 5. So we have 5 cubed times 1 to the fifth power. Well, 5 cubed is 125. And 1 to the fifth power is 1. So our final answer is 125. I showed every step there. You might be able to do this in less steps, but I just wanted to make sure you understood the math behind it. In letter B, we're going to do the exact same thing. We're going to try to evaluate this limit by direct substitution. So we're going to plug in x equals 2. So we have our big radical, and then in the numerator, we're going to have 2 times 2 squared plus 1 divided by 3 times 2 minus 2. Keeping in mind, we have to completely simplify our numerator and our denominator before we do any sort of division if we can. So in my numerator, 2 squared is 4, and then 4 times 2 is 8, and then 8 plus 1 is 9. And in my denominator, 3 times 2 is 6, and 6 minus 2 is 4. And now we can't divide 9/4, right? That doesn't reduce. However, 9 is a perfect square, and 4 is a perfect square. So now we can take the square root of the numerator and the denominator, and we get a result of 3/2. part of our notes deals with evaluating limits where direct substitution is not an option. It sure is nice when all you have to do is plug in an x value and do some math, but this is calculus, not algebra. So most of the time, direct substitution is not going to work because when you try to do direct substitution, you run into a problem. Most of the time, that problem is you end up with something that is undefined. Either you have 0 on the bottom or you have 0 on the top and the bottom. And basically, that's just an indication that you need to do more work, okay? 0 on the bottom or 0 over 0 does not mean an answer of 0. It just means you need to do more work. Let's take a look at example number 4. First, we're going to check and see what happens if we were going to do direct substitution. I'm just going to simplify that to ds. So if I check direct substitution, I'm just plugging 4 in for x and doing the math. So I'm going to get 4 squared minus 4 times 4 divided by 4 squared minus 3 times 4 minus 4. In the numerator, 4 squared is 16, 4 times 4 is 16, and 16 minus 16 is 0. In the denominator, 4 squared is 16, negative 3 times 4 would be negative 12, minus 4 more would be negative 16, and 16 minus 16 gives me 0. Okay, so this is my problem. I ended up with 0 over 0. That does not mean the answer to my limit is 0. It just means I need to do more work. So, based on this, I am going to try, since I have a polynomial in my numerator and a polynomial in my denominator, I'm going to try factoring and see if that gets me anywhere. Because remember, sometimes we end up with a factor that is the same in the numerator and the denominator that's causing that 0 over 0 situation because we have a hole. So if we can cross that out, then we can evaluate the limit. So let's try factoring. This is going to be equal to the limit as x approaches 4 of. In my numerator, I have a GCF of x, so I can factor out an x, and then I have x minus 4. In my denominator, I have an easy trinomial. Two numbers that multiply to make negative 4 and add to make negative 3 are going to be x plus 1 and x minus 4. And then my x minus 4s can reduce. So now this is really equal to the limit as x approaches 4 of x over x plus 1. Now I can evaluate with direct substitution because I got rid of that hole at x equals 4. So now if I plug my 4 in, I get 4 over 4 plus 1, which gives me an answer of 4/5. Let's put a little note here just for our own reminder that we have a hole in the graph at x equals 4, right? We have seen that before. Example number 5. Let's start with an attempt at direct substitution, see if we can do it. Sometimes we get lucky. So if we check direct substitution, we end up with 3 squared plus 3 minus 6 over 3 minus 3. Well, I can see that's going to be bad already. In the numerator, 3 squared is 9, plus 3 is 12, minus 6 is 6, but in the bottom, we get 0. Okay, so that just means do more work. We can try factoring, see what happens. So if I try factoring, I have the limit as x approaches 3 of, let's see, my numerator is an easy factor. Two numbers that multiply to make negative 6 and add to make positive 1 are going to be positive 3, negative 2. And then on the bottom, I have x minus 3. But, okay, this is not like example 4. In example 4, we had the same family upstairs and downstairs, and that was our problem. So we got to cancel them out and move on. Not the case in this problem. This one is different. So let's make a little note here. Factoring did not help. Okay, and this is because there is not a hole in the graph. Okay, there isn't a hole at x equals 3, but there is a vertical asymptote at x equals 3. Okay, so right now I want you to commit this information to memory. If you have the same family, like x minus 3 on the top and the bottom, that creates a hole at x equals 3. If you only have a factor of x minus 3 in the denominator, that creates a vertical asymptote at x equals 3. So it's really important that you know the difference between those two situations. Okay? So problem is, factoring didn't help us, right? But we still need to come up with some sort of a solution for this limit. Since factoring didn't help, let's maybe try graphing. Okay, and I'm going to grab my graphing calculator. I suggest you do the same. I am going to go to my y equals, clear out what was in there, and I'm going to type in my function. Remember, you need to use parentheses around your numerator and parentheses around your denominator. In the numerator, we have x squared plus x minus 6, close your parenthesis, and that is divided by x minus 3. All right, and I'm just going to do a zoom 6. Okay, so we have some sort of rational function here. We can only see one part of our graph. There is going to be another part of our graph up here, and if we make our window a little bit bigger, just make our x maximum bigger, let's go like 25, and let's make our y maximum 25 as well. And let's look at the graph again. There, now we can see the other branch. But what I want you to pay attention to is the fact that right here at x equals 3, we have a vertical asymptote on our curve. And if you wanted to do a second level calculate value and ask it about x equals 3, okay, there is no y value, right? Because when x is 3, the function doesn't exist there. There's a vertical asymptote. Now, thinking about what we know about limits, let's go back to our paper and let's sketch a little picture of what we've just seen. It doesn't have to be perfect, but just enough that when we look back on this later, it reminds us of what we saw. So right here, this is my x equals 3, and I had a vertical asymptote. And my two branches around that vertical asymptote, there's also a slant asymptote on this problem as well, but we're not going to worry about that right now. So we have one branch of our function going like this, and we have the other branch of our function going like that. And so the question is, what is the limit of this function as x approaches 3? Thinking about what we know about limits, as we approach 3 from the left-hand side, the graph is diving down towards negative infinity. As we approach 3 from the right-hand side, the graph is shooting up towards positive infinity. Our limit as x approaches 3 from the left is negative infinity, and our limit as x approaches 3 from the right is positive infinity. And we know the rule, right? If the left-hand limit and the right-hand limit do not equal each other, then our answer has to be that our limit does not exist. So that is the answer to example 5. The limit does not exist. Just like Mean Girls. In example 6, we can start by checking direct substitution. And if we plugged in x equals 0, we would have 4 plus 0 squared minus 16 over 0. We can already see that that's a problem. But in the numerator, 4 plus 0 is 0. Or sorry, 4 plus 0 is 4. 4 squared is 16. And 16 minus 16 is 0. So we end up with 0 over 0. Now, looking at what this particular limit looks like and knowing that I'm not done, I just need to do more work, I'm just going to try some like foiling, simplifying, just basically some good old-fashioned algebra. And I'm going to see if that gets me anywhere. So this will be the limit as x approaches 0 of, if I FOIL out that 4 plus x quantity squared, that becomes 16 plus 8x plus x squared, and then I have the minus 16 at the end, and this is divided by x. Now I can reduce some terms in my numerator. The 16 and the negative 16 cancel out, and then I can actually factor out an x from the 8x and the x squared terms, and if I factor out an x, then I have 8 plus x times x over x, but now I can cross out that x. And then when I do that, that takes care of the problem that I was having before with the 0 over 0. Now this is just the limit as x approaches 0 of 8 plus x, which when x is 0 is just 8. So the answer to example 6 is 8. In example 7, I'm going to begin again by checking direct substitution. So I plug in 0, and I get the square root of 1 plus 0 minus 1 over 0. In the numerator, 1 plus 0 is 1. The square root of 1 is 1, and 1 minus 1 is 0. So once again, I get 0 over 0. I know I need to do something. Based on this numerator, the square root of x plus 1 minus 1, based on that binomial in my numerator, I am going to try rationalizing. But since that square root is in my numerator, I am actually going to try rationalizing the numerator. We're used to rationalizing the denominator, but when we're working with limits, we do whatever we need to do to get the answer that we're looking for. So I'm going to try rationalizing my numerator. So I will have the limit as x approaches 0 of the square root of 1 plus x minus 1 over x. And if I'm rationalizing, remember, I am multiplying by the conjugate of the binomial. So in this case, it would be the square root of 1 plus x plus 1 in the top and the bottom. And when I do that, that gives me the limit as x approaches 0. Now when I FOIL conjugates, remember that the inners and the outers cancel out because they are opposites. So I just end up with first times first, which in this case, the square root of 1 plus x times the square root of 1 plus x, same square root times itself, just gives you your radicand. So that just gives me 1 plus x. And then last times last, negative 1 times positive 1 gives me negative 1. On the bottom, and this is going to be true pretty much every time you're rationalizing to evaluate a limit, we don't want to multiply this x through. We just want to leave it because it's more work than we need to do and it's just going to make things messy. So we're just going to leave it like that with the x in front of that binomial, the conjugate binomial. But notice now that in my numerator, I can cancel the positive 1 and the negative 1. So now I have the limit as x approaches 0 of x over x times the square root of 1 plus x plus 1. And now I can cross out the x's. So I am just left with the limit as x approaches 0 of 1 over the square root of 1 plus x plus 1. And now when I plug in 0 and evaluate the limit, I get 1 on top over, under the radical, 1 plus 0 is 1, and the square root of 1 is 1. So I get 1 plus 1, which gives me an answer of 1/2. So the answer for example 7 the limit as x approaches 0 is positive 1/2. Our last example is example 8. Again, let's begin by checking direct substitution. If we plug in 0 for x, we end up with 1 over 0 minus 1 over 0 squared plus 0, which doesn't even make any sense, can't do it. We just know we need to try something. Now, based on the fact that we're taking the limit of two fractions that are being subtracted from each other, the first thing that comes to mind is to try combining these two fractions together with a common denominator. So basically just doing some rational expression algebra, which we've been doing since Algebra 1. The first thing I want to point out before we combine these together is that the denominator of the second fraction could be factored into x times x plus 1. So when we need a common denominator for x and x times x plus 1, that common denominator is going to be x times x plus 1. So my expression will become the limit as x approaches 0 of something over x times x plus 1, something over x times x plus 1. And the other thing that I do is I always chop slash my negative signs. So this is going to become addition instead of subtraction, less chance to make an error with a sign that way. All right, so now I have to look at my old denominators and my new denominators. If I change my denominator, I have to change my numerator the same way. My first fraction had a denominator of x. Now it has a denominator of x times x plus 1, which means that I have to multiply the numerator by x plus 1. My second denominator, although I factored it, I didn't change it. It was x times x plus 1, and it's still the same. So that is going to stay negative 1. My next step is going to be to multiply out that first numerator. 1 times x plus 1 is just x plus 1. And then x plus 1 plus negative 1 is now my whole numerator, and my denominator is my common denominator. Well, hopefully you can see that we can cancel that positive 1 and that negative 1. And so then we have the limit as x approaches 0 of x over x times x plus 1. Now we can cancel the x's. So this gives us the limit as x approaches 0 of 1 over x plus 1. And now that we've taken care of that problem in our denominator that was causing us to be undefined, now we can plug 0 in. So we end up with 0 over 0 plus 1, which is 1 over 1, which gives us an answer of 1.